Welcome back to the NED series. Last time we completed our chapter number 5, which was of this circular motion. Today, now let's solve some of the questions, practice problems from the past papers for circular motion. So here we have question number 1, and it says the angular speed of seconds hand of a watch in radians per second is what? So, how do we go about this problem? Well, think about a clock. You have a clock, right? And this you have this hour hand, then you have a minute hand, and then you also have a seconds hand, right? Now, this second hand, it would move 1 unit, right, in 1 second. So it would complete its complete revolution in how many seconds? 60 seconds, right? So the second hand completes its entire revolution around this circle in 60 seconds, which makes 1 minute, right? So we are required to compute the angular speed. Now we know the angular speed omega is given by 2 pi by the time period. Now the time period for the seconds hand is 60 seconds, right? This one. So all you have to do is plug in the value of t, which is 60 seconds, and evaluate this expression. So you get 2 ones are 2, 2 threes are 6, and the 0. So we are left with pi by 30. So that's the angular speed, pi by 30 radians per second. So that's our option C, right? So that's the correct option. So moving on, let's look at question number 2. Question number 2 says that the shaft of a motor rotates at a constant angular speed of 360 revolutions per minute. So this angular speed is given in terms of revolutions per minute. The angle turned through in 1 second in radian is. So we are required to find the angle or the angular displacement that is covered per second, and we have to make sure that that's in radians, right? So how do we go about this? So recall that the angular displacement is theta, which is given as the product of angular velocity times the time, right? Now the angular velocity or the angular speed is a constant, and it's given as 360 revolutions per minute. But wait a minute, you have to compute your angular displacement in radians. So first I'll have to multiply this whole thing with 2 pi, so we can get rid of the revolutions. And and we have in minutes, right? So we have this 360 revolutions per minute, so we have to get rid of this minute as well. So we'll just replace, as we know, in 1 minute there are 60 seconds. So we'll replace, you can say that we can replace this revolutions with 2 pi radians, right? So one revolution per minute, one revolution is 2 pi radians, because again, think about this. One revolution is when this vector starts from here and it goes here, 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 and like it travels and comes back to this position, right? So that's one revolution. And what angle is that? That's 360 degrees, which is basically 2 pi radians, right? So that's that. And so what we do from here is we have this thing, and in through 1 second. So what's time? Time is just 1 second. So if you evaluate this, you get 2 pi by 60 seconds radians into 360 into 1 second. So second goes with this, and we are left with 360 multiplied by 2 pi divided by 60. So that's 1 and that's 30, and the 0 goes with this, and this is simply 12 pi radians, right? So that's option D. So that's the correct option. Okay, so let's continue, and now let's move on to question number 3. Let me fix this zoom. Okay, perfect. So question number 3, it says that you have the direction of the angular velocity is along. Okay, so we are given some options: tangent to the circle, inwards the radius, axis of rotation, outward of the radius. Well, recall that all angular physical quantities, right? All angular quantities, where are they directed along? They are always, all angular quantities are always directed along the axis of rotation, right? So you can think about torque, you can think about angular displacement. All of them are directed along the axis of rotation, right? So then the correct option is option C, the axis of rotation. So all you have to do is remember that all angular quantities are directed along the axis of rotation, right? Okay, so with that, we can move on to the next question. So here's question number 4, and question number 4 reads that a disk of radius r equals 20 centimeters is rotating about its axis with an angular velocity omega equals 20 radians per second. So let's just highlight what we are given. So this is the radius of the disk, and it's rotating, about its axis, obviously, and the angular velocity with which it's rotating is 20 radians per second. Now it's rotating on a horizontal smooth surface. Now we have that the linear speed of the point C on the disk is what? So let's look at our disk and let's see what's happening over here. So this is the disk, right? And the radius of the disk from this point, well, obviously the radius of the disk is r, and this O is the center, and we have 2 points on this disk, A, B. And there is one point that we pick, and that point is this one, right? This one, which is point C, and the radius from the center of the disk to this point C is r by 2, so it's half of the radius. And this disk is performing a rotation about the center O, right? So that's the axis about which it's rotating with the angular velocity of omega. Now, we are required to compute the linear speed of the point C. So that's important, right? So we want to compute the linear speed of point C. So for point C, remember the radius is r by 2. So now remember what was the relationship between the tangential velocity or the linear speed, which was it. So the linear speed was related to omega with what? It was related to omega with r, right? So r is 20 centimeters. Now let's write that in terms of meters. So r is 20 centimeters, but what is centi? Centi is just 0.01, so we'll multiply it with 20, and then we have meters, so that's just 0.2 meters, right? Now, what is half of that? Remember, point C is at half of this radius. So for point C, we have r by 2, which is 0.1 meters, right? And so that's the only information that we needed. Now, also know that you remember from the lecture that we did on circular motion, omega does not change at any point on this circle. So it's going to remain constant on all the points, right? Whether they're on the surface or they're inside. So omega is what? Omega is 20 radians per second. So that's the angular velocity. So we just put our values in this expression. So we get 0.1 meters times 20 radians per second. So this gives you the linear velocity as 2 meters per second, right? And so hence the correct option is option B, which is 2 meters per second. Perfect. So now let's move forward to the next question, which is, let's see, it's over here. All right. So we have question number 5, right? And the question reads that if you have a satellite and it's moving around the Earth, it constitutes, we have some options, let's go through them. An inertial frame of reference. So a satellite moving around the Earth constitutes an inertial frame of reference, or non-inertial frame, or neither inertial nor inertial, or both inertial and non inertial. So think about this now. First of all, let's look at this thing. We have a satellite and it's revolving basically around the Earth. So suppose that here you have the Earth, right? And let's say that this is the satellite, right? So here we have our satellite and it revolves around the Earth. Something like this, right? So now if it's revolving around the Earth, what is happening? The satellite is basically revolving, which is revolving around the Earth. It's actually a freely falling object. So it has some angular velocity in this direction, right? But it's freely falling towards the Earth, right? And what does that mean? That just means that the acceleration is equal to g, right? And hence, this the satellite which is moving around the Earth, it constitutes of a inertial frame of reference, right? Because remember that even in this case, there is no net force that is acting on this satellite. That's what it's keeping in orbit, right? So there is no net force. Remember, net is the important word. So there is no net force. That's why the satellite remains in this orbit of this Earth, right? And hence, that's what an inertial frame of reference means. Hence, the correct option should be option A, right? Okay, amazing. So now let's move on to the next question, question number 6. Let me, yeah, so here we have it. Now we have a particle and it moves in a circle of radius 25 centimeters, right? So a particle is moving in a circle which has a radius of 25 centimeters at 2 revolutions per second. So we're given the angular speed as 2 revolutions per second. The acceleration of the particle in meters per second squared is what? So that's what we want to find it in terms of meters per second squared. So remember or recall that the centripetal acceleration, or you can call it the angular acceleration, right? It was given by r omega squared, right? So all you have to do now is put in these values in this expression and solve for alpha. So let's see. We'll use r in terms of meters. So let's get rid of this centi. So r would be, which is 25 centimeters, but we know that centi is just 0.01. So 25 into c, which is 0.01, and meters. So this gives you 0.25 meters. So that's your r in meters. And what about omega? We have to write omega, if we want our acceleration in meters per second squared, then omega must be in the units of radians. So we'll have to get rid of this revolutions, right? And that's very simple because we know that one revolution, again, as we discussed before, corresponds to a rotation of 2 pi. So omega, which is 2 revolutions per second, is simply 2, what revolution is just 2 pi, so we'll just multiply 2 pi, and that would make it radians. One rev is 2 pi radians, and then we have seconds, so we don't need to convert from seconds to anything because we're asked in meters per second squared. So that's this, and this makes it 4 pi, right? So now you have to put these values of r and this thing omega in this expression. So let's do that. So alpha is equal to 0.25 meters into 4 pi radians per second squared. Remember that, squared, right? So if you evaluate this, you get, well, the 0.25 is just 1 by 4, right? And you have 4 pi squared. So this 1 by 4 gets rid of this one of the 4s. So we are left with 4. 1 4 still remains, right? And we have pi squared. So that's the answer, 4 pi squared. And that's the correct option, C. So that's what we'll choose. So now let's move on to the next question. Okay, so here we have question number 7, and it reads that if the position vector of a particle is r, which is this thing, so it's given in terms of these unit vectors. We have 3 I hat plus 4 j hat, right? And it's given in meters. And its angular velocity this is also given in terms of these unit vectors, and that's omega vector is 1 j hat basically, and plus 2 k hat radians per second. Then its linear velocity in meters per second is asked. So we have to find the linear velocity. Now remember that if omega and r are given in terms of vectors, then we can relate them with this expression, which is v, which is simply omega cross r. So it's the vector product of this vector r and omega and r, right? So that's now we have to compute this. So remember again that how do we compute this vector product? We can simply write this as v is equal to, as a determinant, and then you have I hat, j hat, and then here we have k hat, right? Now let's write the corresponding, first we'll put the values of omega. So look at omega, it is 1 j hat plus 2 k hat. So we don't have any I hat component, which means that we'll put a 0 in place of I hat. So here we are writing in this first row, we'll put the values of omega as first we have omega, right, in the cross product. So there is no I hat, so we wrote 0, but there is 1 j hat, and that's a plus 1 j hat. So we'll put 1 plus 1, and then we have a plus 2 k hat. So we'll put a 2 over here. Now let's write down the components of r in this next row. So we see that we have 3 I hat, so I'll put a 3 under the I hat part, right? Next we have 4 j hat. So under j hat for this row, I'll put 4 plus 4. And you see that you don't have any k hat in this one, so that's just a 0, right? Okay, perfect. Now how do we evaluate this? Well, it's very easy. You have to just compute the determinant of all of these. So first we'll write I hat, and we'll put some brackets. Then for every time when you're writing this j hat, you put a negative sign and j hat, right? And then you put brackets. And then finally you have this k hat, so you put plus k hat and this. So remember this format when you're computing a vector product of two quantities. Now, to write down these components for I hat, all I have to do is we'll forget about this part and this part, right? So we'll ignore all of these and then we'll compute the determinant of what's left. So that's 1, 2, 4, 0. So what's the determinant over here? Well, that's pretty simple because you know how to compute determinants. 1 multiplied by 0 minus 2 multiplied by 4. So that's 1 times 0, which is 0, minus 2 times 4, which is minus, or let's just say that this is the minus and 2 times 4 is 8. So this gives you minus 8 iota. Now, similarly, you have to compute the components for j hat, this one. So this time what we'll do is we'll get rid of, we'll ignore these things, right? So we'll ignore this column and we'll always ignore this row. So now let's see what are we left with. We are left with 0, 2, 3 and 0. So now we'll compute the determinant, which is 3 times 2, which is 6, minus 0 times 0. So we have 3 times 2 minus 0 times 0. So this is 0 and 3 times 2 evaluates to 6. So we have 6 minus 6 j hat, right? And now similarly, if I were to do for this k component, right, I'll do the same thing. I'll get rid or ignore this column and all, like always, this row. So these will be ignored and we are left with 0, 1, 3 and 4. So the determinant would be 4 times 0, which is just 0. So this would go to 0. And then we have plus 3 times, minus 3 times 1. So we have, that's 3 just, right? So minus 3 times 1 and this is 3. So what we are left with is minus 8 I hat minus 6 j hat and plus, or we have this minus sign, so remember this one. So we have minus 3 k hat. So that's our answer for V, right? Now let's look at our options. So we have option A, we have minus common 8 iota, 8 I hat minus 6 j hat plus 3 k hat. Now, and then there is, well, another similar option is, it's this one, right? It's kind of similar, 3 I hat minus 6 j hat plus 8 k hat. You don't see something like this immediately, but remember that there is a minus sign common over here. So if I take a negative sign out as a factor, so what I'm left with inside is 8 I hat, right? So I've taken this minus out. This minus also went out, so plus 6 j hat. And this minus is also outside, so we have plus 3 k hat. So this thing is exactly the same as that thing, which is our this option, option A. So that's the correct option. Perfect, right? So now let's move on to question number 8. Okay, let's move this like this. Okay, here we go. So we have question A that says that the mud flies off the tire of a fast moving car in the direction. So we're given some options: parallel to the moving tire, tangent to the moving tire, anti-parallel to the moving tire, none of these. So think about this. You have a tire, right? Here is your tire and it's rotating, right? Let's say that it's rotating in this direction. So now remember that anything that I have on this tire, for example, let's say you have a mud over here, where would you expect this mud to go, right? It would fly off in what direction? It always flies off in a tangent to this point on the tire. So wherever the mud was, it would fly off in a tangent direction to to this point where the mud is, right? So as we learned, or as we saw this in our lecture series, right? So it would just fly off in a tangential direction with the tangential velocity, which was also referred to as a linear velocity, right? So then that means that the correct option should be option B, which is tangent to the moving tire. Right. So, with that, let's move on to question number 9, which reads that a satellite appears to be at rest when seen from the equator. So, a satellite appears to be at rest when it's seen from the equator of the Earth. Its height from the Earth's surface is nearly what? So that's what we have to compute. And we are given this information that the satellite will be appeared to be at rest when you see it from the equator of the Earth. So we know that the height is given by the radius of the orbit minus the radius of the Earth, right? Now, read the statement again that a satellite appears to be at rest, right, when it's seen from the equator. So when it's seen from the equator, if it appears to be at rest, that's what? That's a geostationary orbit. Now, for a geostationary orbit, we know that the radius, let's use small r, it is given as it is approximately 42,000 kilometers, right? Now, what is the radius of the Earth? Well, the radius of the Earth is it is approximately 6,400 kilometers. So all I have to do is subtract this 6,400 from this 42,000 kilometers, and that's 42,000 minus 6,400 kilometers, which is, well, 35,600 kilometers, right? So that's the height from the Earth's surface of this satellite, which appears to be at rest, right? So that's 35,600, and that's our option A, right? So we'll choose A. Perfect. So now let's move on to this final question, question number 10. And this question says that we have a wheel rotates about an axis passing through the center. So a wheel is rotating, and it's rotating about an axis which passes through the center of this wheel and perpendicular to the plane with slowly increasing angular speed. So the angular speed omega, it's not constant, but it is increasing. So that means there is some angular acceleration should be there, right? Which basically means that there is change in omega, right? Change in omega is not zero. If change in omega is not zero, then change in the linear velocity is not zero as well. Well, we know that that's always true, that the change in linear velocity is not zero. At different points, there will be different linear velocity on the circle, and so that means that the tangential component of acceleration, which is delta v by delta t, that is not zero, which means that the centripetal or the angular acceleration, this was the angular acceleration, it is also not zero. And that's because the this wheel is rotating or revolving in a circle. Hence, the angular acceleration cannot be equal to zero. So option A says radial velocity and radial acceleration. Well, but it would also, as we saw, it would also have angular velocity and angular acceleration. So that it does not mention that, so that's not true. Tangential velocity and radial acceleration. Again, it would have tangential velocity, but it would also have angular velocity, and it will also have angular acceleration. So similarly, this would also not be true. tangential velocity and tangential acceleration. Well, that's also not true for same reasons, right? Because it's also having angular velocity and angular acceleration. Tangential velocity, but acceleration having both the components. Now that's more like it, right? So we saw that it has both these components of the angular of this acceleration exist. So the tangential and the angular component also are non-zero. So the correct option would be option D.